with literature and we see that we are reasonably good agreement. We have also used the other functionals to check, but children and we have seen in the literature that ED solid adopted as a solid and it has been proven to be successful accurate results for this. Without any further discussion, all the calculation I have done, we have used PD solid solution. Yeah. Now we come to a next part of the method. So where I will explain you how we compute the response properties because that is our interest. So let me go to directly to the piezoelectric tensor. So the piezoelectric tensor is the change in polarization when you apply strain, and it has two components. The frozen ion part. So the frozen ion part tells you when you apply strain, but you don't allow your atom to relax. So you are getting the response basically from the electron cloud. On the other hand, this is the lattice contribution. So you apply strain and you allow your atoms to relax to that response to that strain, and you get lattice contribution. So in most of the cases, this lattice contribution is the main response, and this lattice part can be expressed like this. So let me explain this equation. So this is your volume of the unit cell. This is the body electric charge, which tells you that how much your polarization gets changed when you displace the atom. Now this is the inverse of the force constant matrix. So that tells you apply force and how the atom will displace. And the last one is force response interaction strain tensor, which is the force felt by the atoms when you apply strain. So now let's see if I can explain you a bit better way. So let me write this equation like this, and as I say that we are concentrating in the lattice part. So I am substituting this lattice part by this time. Now if you perform this multiplication between the force response interaction tensor times strain, you will get force times force constant matrix inverse between displacement of atoms and displacement of atoms times effective charge is the change in dipoles in your system and change in dipoles volume volume is the change in polarization. So that's how we work in the computer and that's how we compute. Okay, and with this, let me focus first on the result of discussion and the first one I will be talking about the physiological properties of hafnia as a function of human concentration. So to study that, what we needed to do initially that we have to choose some dopants, and here we have chose silicon and zirconium because they are isovalent and they have the same valency as hafnium F. So we will be not accompanying any liquid or charge state by that it should be simple situation. And this we studied because they are extensively studied in the literature. So to use long, concentration, low concentration range, we cannot deal with the 12 atom periodic set. So for that we have to enlarge our cells. So we work with the 38 atom cell where 16 are hafnium atoms and 32 are oxygens. Now the question is that depending on the doping concentration, we have to replace hafnium by dopant. Now as you can see there are 16 hafnium atoms. So we were wondering that how do we put the atoms? So for that we have considered several special arrangements and let me mention some important cases. So this is the case where dopant is isolated. This is the case where dopant is forming a layer. So this blue represents the dopants and the yellow are the hafnium. And this is the dopants when they are intercalating between the hafnium. So, except that we have also considered the other possibilities, and just to give you a feel here, I have drawn the space where I have only gave the commands to the so as I said, the yellow was represent hafnium and the blue represents dopant. And as you can see, we have considered quite few dopant arrangements. Next we started calculating the physiologic properties. So here we are interested in the longitudinal visual response. So the value EGG tells you about the change in polarization along the vertical direction when you apply straight along the same direction. As you can see here, I have plotted the EGG versus silicon concentration. And this initially we were wondered by seeing this dispersion of EGG among the configuration is very large. What we realized before understanding this result, we realized that the ordering of the dopant is playing a role. So we did understand whether to trust this result because how you place the dopant inside your lattice, you are getting the response. So instead of understanding these results, first we wanted to understand what is the preferred spatial arrangements of the dopants in Hawkian. For that, I changed my initial goal, and now I was interested in studying the effect of dopant ordering in the stability of derivatives. So to do so, what I did, I considered the ground state, paraelectric state, and the ferroelectric state in 48 atom cells. I consider all the spatial arrangements I have just shown you. And then I calculate the formation energy of each configuration following by this formula. So what this tells you, this is the energy of the compound, this is the energy of hafnia at its ground state, and this is the energy of the dopant oxide at its ground state. So let's say for example A is silicon, then this is the energy of the silicon dioxide in its ground state. So here I have plotted the formation energy as a function of doping concentration. So before explaining the results, let me explain the symbols first. So whenever you see triangle in the graph, that means when dopings are forming there. Whenever you see square, that is they are intercalated between the hafnia metals. And the circle are the other cases, for example, when the dopant is isolated or for example when they are forming this kind of arrangement. So as you can see, the paraelectric phase is the red one and the ferroelectric phase is the yellow. And here each symbol represents the formation energy of this configuration. So at the first slide, what you have noticed that there is a marked difference between the behavior of these two movements, right? So here the energy difference between the least most stable and the least stable configuration are huge. It's around 400 millielectron volt. But here the energy difference is comparatively very less. The another important fact is that here these two phases are really competing with each other and they are occupying the same energy range. But here, as you can see throughout the doping concentration range, the parametric state dominates. So I'm more interested to explore this system and let me explain that a little bit. So here, as you can see, especially at 12.5% and 25%, we have seen the situation where the derivative state is more stable than the parametric state. And now, having found this result, so we were excited initially, but suddenly we realized that some of our simulations gives to a different solution, and by inspecting that structure, we identified that that is the determinal phase, that is another important non-polar phase of this bacteria. So having found this tetragonal phase is very relevant upon silicon doping, we have started doing the calculation for all the doping configurations I have considered for the other phases. So lot of green points here, which of course represent the dielectric tetragonal phase. So yeah, it's sad that the tetragonal phase comes to dominate over the derivative phase. But since we anticipated one question that in 48 atoms is realistic to investigate the relative stability at low doping concentration. Because as you can see here at 6.5%, we don't have any triangle or square. Why? Because that state is not compatible to include known dopants. Like in 6.5% concentration, we just have only one dopant to put. So you cannot see the effect of the ordering in the cell. So to check the effect of the ordering, what we did, we enlarged our cell And now we work with 192 atoms. And as you can see here, even at the lower concentration, we should be able to see the configurations, the various configuration of the dopants. So here, let me mention that all the calculations with the biggest supersets, I have plotted them with the flip symbol. So since we are interested in the low doping concentration, let me zoom in that part. And you see here we have such exciting results that the ferroelectric phase dominates over the two dielectric state, but it has to form layer. So this was the first evidence in the literature where we could see that the ferroelectric phase dominates over the two dielectric state. So once we do the silicon, these points they are degenerate and we want to prove the amount of silicon the tetragonal phase capsule of action. So having found this exciting thing, we wanted to know that what whether this kind of Lewis solution, energy solution. So for that, we concentrated on silicon environment and oxygen environment in our system. And what we have found is that the lowest energy tetragonal phase shows that is silicon O4 formation, and the oxygen is bonded with two hafnium and one silicon. When we have looked at the low lying ferroelectric and the paraelectric monoclinic phase, we have seen that the typical silicon coordination is silicon O5, and the silicon O6 is even seen by the higher order, higher energy line ferroelectric and paraelectric monoclinic phase. So what this suggests that the lowest solutions are those whose bonding topology allow the dopant to form stable bonding complexes. So after that, we also wondered about the polarization because we should not harm the polarization by silicon doping. So as you can see from this table that we have calculated the polarization of the pure material and also for the layer structure at 6.25%. And you can see that we did not harm much the polarization. So we are doing that. And now let me focus on the experimental connection with our theoretical finding, what we used to do. So our theoretical finding suggests that by depositing a thin silicon dioxide layer, we should be able to grow ferroelectric hafnia there. And actually, our finding is consistent with the way how most of the successful ferroelectric things are grown in the literature using atomic layer deposition. So in atomic layer deposition, what you do is you perform a dopant oxide cycle after 3 to 1 oxide cycles, and then the film is subjected to annealing to induce crystallization. And in that point, you may assume that the dopant retains inside the lattice, but there is evidence in the literature that they have seen that there is a diffuse silicon layer in your sample. So what we understand that by controlling, maybe it could be by controlling the layering of the small dopants would be the key to produce better samples. So here let me mention the previous first principle study where they said that doping itself is not enough to stabilize the periodic phase. And because they have ignored the important fact that they have such preference towards ordering, and indeed this study proves that doping does not locate randomly at the lattice, and that assumption was appropriate. So this let me summarize this part. So ferroelectric state can be a ground state with moderate silicon doping with the silicon dopants forming there. And if this is true for the silicon, small dopants like silicon, we have also checked the other small dopants, for example, germanium. And we have seen that preliminary calculations suggested that similar behavior also has been seen by other dopants, for example, germanium. But as you see from this result that the Sonian shows very weaker tendency, and that is also true for other lead dopants. So the main take-home message from this study is the ordering of the dopants, especially the silicon-like dopants, matters to stabilize the ferroelectric phase, and certainly it changed our way of thinking about dopants inside the outside. So with this, let's go back where we started from. So the physioelectric properties of coffee as a function of dopant concentration. And this time, let's see if we can understand the physioelectric response. So here I work with the system polarization pointing upward. So as you can see from this figure, one fact what we did not pay attention to it before, that we are getting negative EKG. So in usual case, so for example, in peroxide, what happens when you apply vertical stretching to your cell, you expect your polarization to grow, and thus your EKG is positive. But here, this negative sign of EKG suggests the opposite. So we asked ourselves that before understanding the physioelectric coefficient as a function of protein, did we understand what is happening in the pure system, why it is negative there? So again, I changed my idea and I went to the way to study the physioelectricity in pure. To understand the peculiar behavior of this material, we consider a model ferroelectric lead platinate and hafnia in its ferroelectric state where the polarization is pointing upward. And I calculated the ECG coefficient. So from the table you can see that lead platinate has positive ECG and hafnia has negative ECG. So and this sign is coming basically from the lattice, which is dominating. So while struggling to understand this negative sign, or whether we are computing things correctly or not, we have found one article in the literature where they have also confirmed that yes, Hafnia has negative usage. But the physical picture was not satisfactory, so we wanted to have a simple explanation behind why it is negative. So to explain that, let me again go back to net net part. So net net here, this is the parametric phase, and these arrows represent how the atom moves from a paraelectric to ferroelectric phase. So as you can see that all the cations are going up and the anions are going down, so you are getting a polarization point upward. Now imagine you are stretching the phase along the vertical direction. So here this green arrows represent how the atom reacts to that stretch. So as you can see that, for example, if we focus on the titanium and oxygen, they have some suitable bond there. So while you are stretching, the titanium would like to maintain the bond with oxygen. So further it is going further up and the oxygen is going further down, and as a result you are getting a polarization, increment of polarization, and which is giving you positive sign of it. Now let's see parallel what happens with hafnia. So again, this is the paralytic phase, and this is how the mineralization goes due to the downward movement of the oxygen atoms. Now let's do the same thing as we did here. So we are stretching the cell along the vertical direction, and now what should we expect? So if instead of going this oxygen is down, it is going up. So it is going back. And this going back is against this movement when this the very same atoms created polarization. So this gives you a decreasing of polarization in your cell, and as a result, although your delta eta, that is the state you are applying is positive, delta p is negative, and you are getting negative sign of it. Why does this happen? To study that, I focused on the local bonding mechanism of the atoms. So here I highlighted few atoms, for example, this oxygen atom, which has three nearest electrons. And as you can see from the bonding that it may look that they are almost similarly strong. So to understand that, we have calculated the charge density distribution, and from this we can, I don't know that whether which bond is stronger. So they are almost equally strong. So now imagine that we are stretching the cell. So how this oxygen atom should move? Should it move up or should it move down? But importantly, one thing you should remember that while we are stretching, this bond will be mostly affected because this is the vertical band bond. So to preserve the bond, this bond length, these oxygen atoms will move, and again this is the opposite to the delta point of the polarization. So what we were wondering that due to this upward movement, we are getting negative frequency. So it seems that this bond is the important one. So we can make a hypothesis that By weakening this bond or by strengthening this bond, we should be able to affect the magnitude of our piezoelectric coefficient. So let's see if that hypothesis works. So here to affect that bond length, the magnitude of that bond length, what we did, we applied epitaxial compression or expansion, and we allow the outer plane lattice parameter to relax. So here I have plotted the bond length versus epitaxial strain. And as you can see that once you more and more compressing the plane, you are getting out of plane bond length increase. And this is the out of plane bond. So yeah, we get the result control of this bond length. And now here note that we are at the same polarization state. So that polarization grows, but we are always at the same polarization state, which means that polarization is always pointing upwards. Now we see what happens with E3G coefficient. So here I have computed the E3G and each strain values. And as you can see, although the frozen iron part is nearly constant, but the lattice part we are getting, the lattice part is changing. So for that, here, as you can see, once you shorten, weakening that bond, you are basically doing, decreasing the negative effect of the HEG, and once you make it strong, you are increasing the negative effect of the HEG. And very excitingly, at some point you notice that even we could switch the sign of the HEG. And this was very exciting because this has never been seen in any derivative. So let me explain you the sign behind each HEG. So for that, let me focus on the limiting cases. So for the 7% compression, where you have the most positive HEG, let's see what happens. So here, once you compress in plane, you are increasing the out of plane bond length, right? So here now this oxygen atom is more trained with these two oxygen atoms. So as a response to the strain, it is moving down to make these two happy because this is already you have made very large the length. And since this is the direction when this atom moves and you grow polarization, so by the downward movement of this atom, you are basically enhancing your polarization and you are getting positive results. Similarly, with the pure system, if we try to explain the another scene, like at the very negative or limiting case on the other side, where we have the most negative HEG. So here we have reduced this water. So now this oxygen is more trained with these two hormones. Now if it goes up, it can make it happy. If it goes down, it can make it happy. Now how it should move. But again, with the same logic, this bond will be much more effective than the other one when you stretch particle. So it will move up, and this movement again is the opposite to the direction, and you are getting negativity. Thus, our this physical insight suggested that controlling the we can control the atomic environments of the piezoelectrically active atoms, and by doing so, you can enhance your piezoelectric response. You can reduce it, and even you can switch the. So, in the course of this work, we have conducted with an experimental group in University of Nebraska, and they have measured the piezoelectric response in hafnium. So they have considered two other reference materials. So previously is the peroxide oxide, where it is known in the literature that it has a positive value of piezoelectric response 6 And let me tell one thing that B3G is a quantity that is easily accessible in the experiment. So we measure that in the experiment. So BJP has negative positive TGG and PVDF is a ferroelectric polymer and it has a negative TGG. So they have performed this measurement and this clockwise rotation denotes the positive sign and anti-clockwise rotation of this loop denotes the negative sign. So as you can see that Hafnia has an anti-clockwise rotation which indicates that it has negative TGG similar like PVDF but opposite to PZT. They have computed the effective TGG and which is -2 to 5 experimentally. So to compare with their value, one fact we have considered that in most of the experimental field you have polycrystalline sample. So your grains are not properly oriented on a particular direction. So for that, we have calculated an effective average. And as you can see that we are well matched with that. However, there is evidence of having positive density in the literature. So people have found positive density in those samples in Hafnia and in literature. Thus, we think that the longitudinal period response in Hafnia is sample dependent. And more systematic study is needed to figure out what is going on experimentally to which is controlling the sign or the piezo response or the magnitude. So with this, let me summarize this part. So here we understand the negative longitudinal visual response of apnea. We predict that you can prove this by application of epithelial strain, and most interestingly, even you can switch the sign of the ECG without switching its polarization. So to our best knowledge, this is first ever ferroelectric strain discrimination. So again, I went back to the study I started with. So piezoelectric properties of apnea as a function of dopant concentration, and let's see if I can show you something. So yes, finally we have obtained some results in this study. So here we consider the isovalent dopants, and you see that the dopants they show very different behavior. And here this study is focusing on the dopants configuration where dopants form in layer. So this study we are still trying to understand, but let me mention quantitatively at least. So you can see that the dopants which are smaller than hafnia, the negative effect has been reduced with increasing the doping concentration, and opposite happens with the other dopants which are larger. So quantitatively, we would increase the physiological response 47% by lead doping and 22% by zirconium doping. But qualitatively, we are still trying to understand the reason behind that. Okay. On the other hand, we are also interested in studying the isolated case. And here we will see that the different behavior, very different from the what we have seen in the layer structure, and it increases maximum per silicon dopant, but we are still figuring out. So with this, let me show the list of applications what this PhD has left. So these two works I have just explained you, and this is the work we have done in a collaboration with an experimental group where we studied another polar polymorph of I mean, it has been proved that the hafnia also presents another ferroelectric longitudinal phase. So in this study, we have done the similar thing in zirconia, and we have helped them to understand that result by the first principles calculation. And in this, which is in preparation, we are currently preparing the manuscript, and we studied the ferroelectric longitudinal phase in hafnia, and at least at the fundamental level, we have found very interesting phenomena there, where there is a competition going on between improper and highly improper ferroelectricity. But I cannot, and I don't have time to explain that in detail. So sorry for that. And with that, I would like to conclude my talk with summary and conclusion. So here what I want to focus that what was not done before and what advancement this thesis has made. So first the scalability of the periodic phase. So on the first instance existing study they have thought that doping itself cannot stabilize the periodic phase, but here we have found a strategy where you can stabilize this phase with doping, but it has some special height. On the other hand, the negative longitudinal visual response. So when we started, there were no report about it, but after that, few results have been published. But we should understand the physical picture. Here we have provided the physical origin of this negative response, and it also predicted that it is differently related to texture strain. And we have also made some effort to optimize the visual response, although it did not qualitatively understand the result, but at the quantitative level, as you can see, we have tried to enhance the visual response of our. Thus, we believe that we have made some progress in this field in terms of quantitative knowledge. With this, let me briefly mention the outlook. So here, having found this interesting behavior in apnea autonomic phase, paralytic phase, we were thinking that this kind of study can be conducted, for example, in other polar polymers, for example, as I just mentioned, the rhombometer phase. And simply we can repeat for zircon also, because who knows, maybe zirconia could also be a exotic paralytic like apnea. And since here I have only worked with isovalent endorphins, but we can also work with the other experimentally varied endorphins, for example, lanthanum or yttrium. But most importantly, what I want to tell you today is the broader or deeper relation I have learned from this work. Is Hafnia is a very unique terminology, very different from derivative peroxides. So there are ways you can use Hafnia, properties of Hafnia, you cannot even imagine doing with peroxide material. And so from the beginning, when we will be working with Hafnia, we should be careful and we should not imagine that if we follow the trend in the peroxide industry in the literature. And maybe there are opportunities to explore its unique tuning properties and who knows, maybe probably more satellites that comes up. So with this, I'd like to thank my jury members for accepting to review my thesis. I would like to thank my supervisor for his support throughout my PhD and his guidance. Special thanks to Hugo who has helped me a lot in my PhD journey and I have learned a lot of things from him. Thanks to Natalia, I have worked with her and learned so many things. And finally, our theory team. So we have so many useful discussions which helped me to acquire more knowledge and all the new and the old members of our event group. And finally, I would like to thank my family and friends. Without them, we would have not been possible. Thank you for your attention.
স্ক্রিনটা তিনবার অন করা আছে গুড আসছে তো ভিতরে জানমান কি পরে স্ক্রিনটা তিনটা ওরা ভালো ওই জন্য একটা
Okay, thank you for the presentation. And now it's time to come to the second phase of the defense, questions and answers. And the tradition to start with the person coming from furthest away. So, joining remotely from furthest away. So, Julia, are you ready?
Yes, thanks. Okay, yeah. Thanks to Sangeeta for a very clear presentation and very nice results. So I have a few questions. Some are more technical, some are more general. Um, so I will start with one on the piezoelectric part, right? Because you show that there is a negative longitudinal piezoelectric effect, and also, which is very unconventional, and also you show that you can actually cure it, right? So you can switch the sign depending, for example, on strain or silicon concentration. So I was wondering, and so this is very exotic and very unexpected, right? But is there any application that for which you would need a negative longitudinal piezoelectric effect? What would be, why could it be useful, for example, for something that for which you can switch the sign or are it negative?
Okay. So actually, when we have studied this and having found that it has a negative effect, initially we were interested to understand at the fundamental level that what is going on because it is not common in other electrics, for example, in peroxide. So at the fundamental level, we have tried to understand the physical reason behind it. And when you can switch the sign, it should have some applications, but In that regard, we didn't think much, but it was fundamentally very interesting that we could switch the sign even without switching the polarization.
Okay. And in this, along the same line, if I understood correctly your reasoning, you mostly related, let's say, the positive piezoelectric coefficient in lead tightening to having like a perovskite structure in the diagonal phase and trying to keep the same strong bond length when you strain, right? And in Akimoto, doing something like this would lead to an opposite effect. So in this respect, I mean, would you generalize? I mean, is it allowed to generalize the positive piezoelectric coefficient to a tetragonal perovskite and a negative one to a orthorhombic acmimotu? For example, I mean, if you do rhombohedral acmimotu, or if you do orthorhombic zirconiomotu, do you expect to get something similar, something negative, or not? I mean, can we generalize, let's say? So it's negative because it tries, it has this arrangement of bonds, and so it tries to keep the same, bond length. And so if I do zirconium 2, I probably get the same. But if I do it maybe rhombohedral, when the pattern of bonds is different, maybe I don't get it negative. What is your, do you have any, comments on this or thoughts or?
Actually, in hafnium, basically, the atomic environment is very complicated, and the movements of the atoms in an external response is very unpredictable. So, like when we are applying strain, but behind the getting the negative longitudinal response. So we initially tried to understand by looking at the quantitative charge, for example, and the other parameters. But what we understood from that lambda tensor, what I have explained you that the force response internal state tensor, since it is dependent, the lattice contribution is dependent on that. So we were monitoring that how the atom moves. But what is your question is that can it be same way we can explain the other polar polygon? For that, I would say that we need to really check the atomic environment of the atoms inside that phase, for example, rhombohedral phase. And by looking such tensors, we can understand the results. But I mean, since it's very unpredictable, so I cannot give you that surety that you can see the similar things in rhombohedral phase.
Okay, good. Yeah, thanks. And about this silicon ordering, this I also find very interesting. The fact that you get, tendency towards ordering people at least for some components, right? For silicon. And you also show that actually the silicon, putting a layer of silicon doesn't, let's say, doesn't negatively impact on polarization. So I was wondering if in the silicon 2 layer that you are, is there an offset? I mean, does this silicon 2 layer somehow contributes to polarization or not? It's strongly paraelectric, so that any ferroelectric distortion doesn't propagate to the silicon 2 layer, or it does. So if you do like a layer decomposed polarization, would you find contribution from silicon 2 or not? Was that clear enough? So I don't know, maybe, I try to rephrase it. If you look at, for example, the silicon 2, do you see some offset or not?
Actually,
For the,
while trying to understand these results when we put dopants, we have tried to decompose layer by layer to understand what is happening and what is controlling the sign of the HTT. But specifically, I did not look at the polarization of the silicon layer, but that
But it's not too hard to get it anyway, right? Because you show that the polarization, I think you have some results showing that it's basically, yeah, almost the same, right? When you put a silicon layer, so it's not too different. Okay, okay. And also, yeah, about this, because of course from VFD, we are always concerned that when we build a system, there are different, strategies that we can choose to select the structure, right? So my question is, okay, there are two kinds of dopants, probably, right? Silicon or germanium, which are more, yeah, belonging to column 4, and then maybe zirconium, which is like a transition metal, so belonging to the same column as carbon. And so my question is, you examine many, well, let's take silicon, for example. You examine many configurations, because you took this 48 atoms and you really did a very careful and systematic analysis. But my question is, did you think about, like doing molecular dynamics or genetic algorithms, let's say explore, let's say, let's say even in a wider way, some possibilities for alternative structures.
yes, so we did not think about such other possibilities here. What we have done is manually we have arranged the atoms inside the cell and we did the calculation. But in principle, yes, genetic with a genetic algorithm, you can make it more systematic so that it will not require your inputs and it will be more systematic and you can explore the more possibility of the configurations. But in this study, we didn't do that.
Yes, good. And also for this editorial, I was wondering if you consider, for example, the special quasi-random approach, or that can, like giving, let's say, a very close to completely disordered system, even keeping a small, relatively small number of atoms in the unit cell. It's very systematic, right? So I certainly appreciate that, but sometimes, we get this, when we try to, when the people try to approach disorder system, generally, it's, we can get comments from, and that, we didn't explore completely the whole, phase space. So I was wondering if you think, if you thought about this alternative approach, which is, and if you expect that you will get into the different results, let's say, if you feel confident, let's say, on your, DFT static calculation, or you think that maybe, I don't know, you could get different results if you if you use a different algorithm in the structure of integration in the end. That's probably the general question.
Yeah, so that's really good question. But I mean, in the course of this work, when we initially wanted to study the physiologic properties as a function of dopant, but then we realized that it has really strong tendency towards ordering, and then we we systematically what was possible to do manually. We have considered several arrangements of the documents, and if you look at the energy range, for example, uh, we can see that the this huge dispersion among the configuration. So yes, you are right that we can make it more systematic by using other possible way. But I think that the results will not change much because we have already considered good number of configurations, and the trend will be, I mean, more or less same, maybe with few more different points.
Okay, good. And then I will some general questions since you work for long on this Hakimoto and some, it has been also discovered already like a decade ago. Sometimes people refer to like the ferroelectric of the future. So I was wondering, what is your opinion on that? It's very general question, right? Because you're an expert on the topic. So I was wondering, what do you think about, Hakimoto being the ferroelectric of the future?
Yes, indeed, I agree with you because it has so many useful properties which could be very useful. So, for example, as I have explained in my introduction, that it could be very useful, for example, in the microelectronic devices and or the memory technology. And you can use this property the way you cannot do it with the perovskite, which is the mainstay, let's say. Now, in future, maybe by tuning the property of this material, you can use it widely. And
And I was also curious to know what is the result you're most proud of among the many results that you have.
uh, so the most exciting thing was I did both because ordering of the documents affecting the stability was not very obvious or was not found before. So it was exciting, but if the I looking at the negative piezo response, initially we didn't believe it, and we tried so many things to confirm that whether it is actually negative or not. So that part was very exciting, and to understand that why it is negative by looking at the songs, and it actually changes our way of thinking about the physioelectric properties, what we understood from the perovskite, for example. So yeah, that part was more exciting.
The final question I have is generally, the hafnium, have people do calculation about hafnium O2 and then zirconium O2 rather often shows very similar behavior. What about titanium O2? Do you think it's similar or it's completely different? Because it's in the same column, it's a transition method and it's much smaller. And you also showed that, eventually many of the effects are probably related to the size and the ionic radius. So I was wondering, given the fact that it's, you didn't do calculations, so but in your feeling, is titanium also completely different from the other two, or similar, I mean, in which respect?
I would say it's not I feel that as zirconium and hafnia, it should be different because zirconium and hafnia have very close nucleus and the atomic environment. If you see both the materials, they are very similar, and the coordination of the atom and the way they respond to inside the lighting, it's very similar. But I think titanium would be different. I guess.
Okay, yeah, thanks so much for answering my question. Thanks a lot for the clarification.
Yeah, thank you very much, Sylvia, for your questions. And I'll pass now the word to the second speaker, Dr.
Thank you. So, thank you. The manuscript is extremely readable, it's short, thank you, and concise, but it's very clear and presentation as well. There are many things in the manuscript you didn't bring up because they would complicate the story, but I will do the opposite, but I will start with more general questions. So you have a very nice breakdown around page 10. You list all kinds of challenges in the field. And I'm not entirely sure if you have answered all those challenges or not. Can you tell me which of those you think about wake up and all these other things that were very specific to, very technological? You can feel it during this, right? But which is outstanding, which can you actually address with PhD, and which are just problems for someone else?
In presently, the important issues in hafnia, which are the stability of the periodic phase. The another one is the wake-up effect it needs experimentally. And the last one is the piezoelectric response if we can enhance it to be able to use as a piezoelectric. So here in my thesis, what I have addressed is stability issue in my first study where I have shown that experimentally it has found that dopant can facilitate the formation of the periodic outcome. But we have later seen in the first principle calculation that it is dominating over the other two important paraelectric fields. So here I gave some insight in that matter that by considering small dopants and by atomic arrangement we can do something in that level and maybe experimentally if you want to correlate with that you can able to produce better samples. And the next issue, which is the chemistry of useful piezoelectric. For that, before thinking about the application, we should understand what is happening fundamentally, and we can then think that what are the ways we can tune if we understand what is going on, what is the responsible factor which is controlling the property. So in that aspect, in my case, I have addressed that we gave gave a simple explanation, let's say, by which you can tune the properties of the material and by atomically affecting the atomic environment of a particular physiologically active atoms, let's say. And the another thing we were interested in how much can we enhance the property that it can be useful as a physiologic. So since I have told you in the introduction that if we think about aluminum nitride, so let's not go to the PhD. If we think about aluminum nitride, then the piezo coefficient in pure material is around 4 to 5 pair per volt. So in hafnia, we have in the pure material is close to 1 point minus 1.5. So we tried with the dopant, but it complicates the thing when we use dopant and then the atomic environment is very difficult to predict and give a simple explanation. So, but at least at the quantitative level, we could enhance the property. And the last issue is the wake weightage. In that regard, we did not study anything in these cases, but I don't exactly know that how can it do that with DHT because it is mostly believed that in the experimental sample we have a lot of oxygen vacancies which is to redistribute them you need to cycle the samples to have related to the polarization. But with DFT, maybe we can try to see the effect of the oxygen vacancy and how it affects the stability because indirectly the stability can give you the answer that what are the effect of the oxygen vacancy in stability and then maybe we can do something in that regard.
Okay, my question was slightly broader because I read the chapters and they answer the problems that you posed at the beginning. Um, in the healthy technology, are there other issues that are still not addressed or if they trust your work and use it to optimize the processes, are we really, in business with happening for applications? Are there other things that are waiting in the wings that might be problematic?
In that this work can help.
No, this work definitely is help. Now that we know all this, are there still roadblocks we can have now in certain applications? Other things you didn't mention in your introduction? Or it was just really all of it in the technical difficulties or problems? Yeah. These are what everyone complains about and is working.
Yeah, I think these are the main issues in the literature, and maybe if we want to do something new, would be there will be more issues we will be
Always. Okay, some more specific questions. You show a number of different structures and you focus on local environments, which is very interesting. And you have a huge variation of local environments with threefold oxygen coordination and coordination for happening, which goes from like 4 to 9. How do you explain the huge variation in all these coordination environments? With an idea of why it's so variable and it doesn't go completely amorphous or something?
that in all the workshops why it is varying.
Yeah, typical coordination is fourfold or sixfold. We understand on the basis of simple chemistry, and here you have this huge variability. And none of your phases become static either, right? So this remains kind of like an covalence bonding, and yet the number of electrons you're sharing all over the place is extremely variable with the different phases. I'm not saying I have an answer, but I found it really bizarre.
Yeah, like Hafnia has like at least at the theoretical level, it has close to like 18 polymorphs.
Mhm.
Yeah, I have noticed that coordination of Hafnia with oxygen varies from one polymorph to another.
You can do this with silicon as well, but you have to do it under extreme pressure. And then you get sixfold or weird coordination numbers and so on. That you can understand these really important things. But here you're not. It's always at zero pressure. It's still extremely polymorphic. Um, so this is really a good site. You did this in steps, and in each step it was disappointment, and then we found something new, and now you stop. Um, are you worried that you might find yet other phases in the line of what you were saying before? If you went for some genetic algorithms and allowed for full variation of the crystal structure and everything else that are even lower in energy. All this is about like 100 million above that. you might want to segregate and so on. Are you sure this is the last word and that the layering is really the most stable phase, or do you stay awake at night because maybe there's another round of people or other phase that's it must think up?
If we see the energy differences in the, let's say, pure material, then close to this ground state phase, these two like derivative orthonormic and is very close, but Rampometer phase is not that close in energy. So I would not expect the Rampometer will become so dominant that
Yeah, that or anything else, right? It could be something completely unexpected, spontaneous, or whatever. So you
polymorph for the list of polymorph, if you see their energy with respect to the
in a pure system, but as soon as you go to look at the tetragonal phase, it becomes the most stable one when you go a lot.
yeah, and it is also consistent with the experiment like mentioned, job series and performs with the experiment that it cannot be papers. But I mean, of course, with genetic algorithm and if you explore the whole space, you could get
And
certain.
we've explored the stoichiometry down to low concentrations just by expanding it in one specific direction and allowing for layering of the dopants. That feels a little bit like you're selecting the direction in which you're going to search. We didn't try any larger but still somewhat cubic shaped cells with random positions of the dopants to see if that also was interesting.
So in this, before going to the large supercell, here we have noticed that few spatial configurations which is energetically favorable, for example, the square one where it is intercalated and the triangle one when it is not there. But then it was the next step was like we wanted to achieve the lower doping concentration and this was the simplest possible solution we can give that.
If you have about 200 atoms, you could also make a cube instead of expanding just in one direction.
Yeah, but if I want to explore the effect of the layer, then in
Yeah,
that
I'm not saying don't do this, I'm saying maybe it feels like this is a kind of segregation, right? Your all formation energies are positive, and so the thing you really want to make pure apnea and separate out the silicon and two, and that's kind of what it's doing. But you could also imagine more same dilution, but random distribution of silicon, and that might be just a concentration effect and not necessarily a ordering effect. In this same unit cell, you could also put the silicon randomly in the columns.
yeah, I mean here I have also done that with like that square which is represent almost an intercalation where the dopant is not forming there, but that is higher in energy forming there.
For some of these, you find, I think it was later on, you find the polarization of something like 50 coulombs, right? Um, this is in, so 625, this is in the really big supercell. Does it depend on the size of the supercell? You get something similar for the small one and the same order in silicon?
Calculated with the smaller cells, but when I am using smaller cells, so I have computed for example at 25%,
Mm.
and I get around 46 microcoulombs.
Okay, that's not too far. I was a bit worried that the polarization quantum might depend on the supercell you choose. And so it might be a little bit random because experimentally you won't have the beautiful planes that are completely flat and spaced exactly by, I don't know how many angstroms. And you'll have something a bit random, and if that then affects the polarization that you get out, this is only first guess.
Yeah, experimentally, like if we compare the polarization in the pure material, then the agreement is good, but of course we cannot expect the same value.
What do they get?
We get maximum 40.
Ah, stop. All of this concerns the internal energy. What you do is T equals 0, punch down internal energies. But these are all made at quite high temperatures and used at room temperature, I imagine. Have you looked at all at including other effects in thermodynamics to estimate how much this picture can change with respect to the kind of formation energy curve? How much might that shift if you were to take into account the entropy? Because there is no entropy here.
So we haven't done that, but in the literature, seen some results where they have considered the internal energy and the gives free energy. But in that, in the pure material, they could not like find any noticeable change in the difference in the energy between the protocols. So
There's no change in the order of the stability or what?
yeah, order is difficult.
Because when you start doping, you have other sources of entropy, right? You have a very different system. If it's pure, then you look at the different phases, you might have a phonon entropy or something else, but when you have many more configurations, when you start explaining your diagrams and all the positions for the system, and the perfectly planar one is really a very specific single configuration with a very low entropy. And this will favor all of the other ones. There's experimental evidence as well. It's just that it would be useful to have an estimate of how much this is. And maybe you can do it just on the basis of playing around with the energy differences and looking at the number of configurations we have. In the so one or two questions about the piezoelectric effects when you start doping. I imagine you relax the structure and then you look at the strain effect and so on. Before you relax the structure, do you have an estimate of how much the dopants are actually inducing some kind of internal chemical pressure on the system? Can you give me a number compared to the stress you have to apply in the other case? You see what I mean? Before you relax, you take your system, you dope, and you just look at the total energy, and then it will induce some forces, and it will induce some stress on the system. Do you have a number for that? Or can you tell me how much it expands or contracts compared to the pure system?
So for example, this is the case. So this is the case when I doped 25%.
Mm-hmm.
And we can see that the lattice parameters are changing from, for example, compared to the pure system. If you see at the silicon doped system, then it is a contraction in the lattice parameter.
It should be the same, and the dopant is just affecting the internal strain.
Yes, and also understand the piezoelectric response of the dopants. That's what we have done. Like we wanted to understand whether it is coming from the strain it is creating in the lattice or it is due to its local environment. And in that study, what we understood is the local dopant response is the dominant factor.
Wait, say that again? I didn't quite understand these diagrams in pieces here.
So this is the pure chocolate.
Mm-hmm.
And this is the calculations, so where I want to see the effect of the strain. So I keep the same of the dot system, but I consider the pure hapnia and I relapse them in the same relapse position. And on the other hand, what local dopant response is giving, like I take the hapnia state, so there is no cell and we get doping the dot.
Yeah, I was okay. Okay, that's fine. Thank you.
Thank you very much, Matthew. And I can't work.
Anu.
Okay, thank you, Luca. The Sangeeta was really nice. I appreciated the talk, it was very clear. So, of course, very much appreciated the CT, but what we see that later. Some questions on your work. I will start also with the PhD paper, of course. I think in one of your slides, when you showed it, I mean, I like also the way you showed it, slide 41. So, I like the way you show the overall strategy. Yes. But when you said that when you look at 25% concentration, you see that there's a large spread, and then you say, I have to understand now what's going on and why do we have such a breadth in terms of the properties. But something that just caught my eye is with Sylvia, you were discussing the values and I mean, the interest of having it negative or perhaps also finding a way to switch from negative to positive or etc. But I mean, me as an experimentalist, what I'm most interested in is the absolute value. So here, if I look at the maximum value you can have, I don't know if it is significant, this is my question, is the value at +10 coulomb per square meter is significant? And if yes, what is the configuration that you have here?
I mean, so this was the very preliminary results. So before we understand the ordering, so I have done this calculation for all the arrangements. And this, I mean, I think we cannot trust this result because some of the polymorphs are very high in energy, and we cannot trust that result that because of the high energy you're getting huge.
Okay, so you wouldn't just you want to share my optimism on this.
And are the most unstable ones the ones that have that largest TP3? Because
Okay. All right, very good. Other question on this to also somehow jump on what Matthew mentioned. So because I had also this, I'm not very familiar with this chemical pressure, but I saw it some years ago. I read a paper that was on very strong pressure that was applied on PTO, if I'm not mistaken. And then there was when you pressed very hard, very hard means 50 gigapascal, for instance, or even more than what you have here, you can generate some phase condition and even some phase, if I'm not mistaken. And I remember in the conclusion of the paper, rather than applying such massive pressure that on application is difficult, they were mentioning this notion of chemical pressure, that rather than doing this, you would then trust a bit in the spirit of what you said, that you would choose documents that would be either smaller or bigger, just to somehow play this role on the core structure of apnea and doing it. So that's first point. Second point is that indeed, so we always discuss this with Jorge, the strain that you need to see this nice effect of changing the value of each district is really, really massive in terms of, except if you have a few layers where you can probably afford that. But otherwise, as long as you want to have a device which is big enough to measure something, again, I'll put the transistor aside because here that this is really interesting. But if you have something big, I mean, it will be very, very difficult to have such a strain in the material without affecting it. So, is there I don't know, kind of other strategy just saying I am going to use isovalent tokens to investigate more this notion of chemical pressure on this. So for instance, I don't know, using two different atoms to compensate the charges. Is it something possible to avoid or that address this or
I think that maybe this huge chain is not experimentally it's huge, but one thing we can think of that apnea is like very hard. If you look at its elastic constant, it is harder, much harder than the perovskite. So that can allow us to apply more strain than what we do in the perovskite. But I think if we can combine like repetition strain and dopant, so the both effect would give us like we don't need to apply that much strain because by other dopant we can also reach that ratio to what we want. And one thing what we can I can mention that for example I haven't talked about the monitor phase. So there experimentally they have grown that phase and there if we compare with our theoretical result, then it is matching with almost 55% repetition. So which indicates that probability is possible to apply that strain now.
Okay. Well, I'm moving in this direction. You talked about the value in nitride, this scandium, and actually when you dope this scandium, you decrease very much the younger use of aluminum nitride. And that's also a way somehow to increase the physical expression as well. So, another question, and it could be my last question. I think that in the challenges that are in the future or current challenges for apnea, there's one that you didn't mention already, but this is the coercive field. And to me, that's probably, especially for the memories which remains from now, the main application that can foresee in the future. But that's very close to break down it as well. Same problem as what people observed in aluminum nitride and the scanner to observe also this CP. You are very close. So the question is, did you by chance see a decrease of this coercive field? I don't know if you investigated it, but by doping or with the strategies that are in place for the piezo, do you see an effect also on coercive field?
We did not study that in this. But yeah, I mean the effect of electric field is something you can study using DFT. So you can like as I was explaining, it seems that the oxygen vacancies are playing an important role even in that huge force field. So what we can do, maybe we can see with the application of electric field how and where they are getting migrated inside the lattice and how that is affecting the stability.
Okay.
but it's, I didn't understand that it can do it.
Okay. Okay, great. Thank you very much again, Sanita. And discussion.
Hey, thank you. Before I pass the word to the supervisor, I have a couple of questions myself. And maybe my main question was this atomistic insights, slide 45. So there you argue a little bit hand-wavingly with the strength of bonds and to visualize the density and with the numbers of the bond length. Is there a way to do it more, or to discuss maybe other possibilities to make it more quantitative, the strength of the bond? I mean, the chemists, they have measured like the bond order strength, there are codes that calculate this, post-processing from plane-based calculation, or the electron optimization functional to think of any discuss if one can make it more quantitative.
Yes, what we wanted to understand which bond is strong by looking at the charge density, but one thing I can show you is we have also computed the line profile. For example, if you start from an atom and you are computing the charge along your bond, and you reach to the another atom, so that distribution of the charge density can tell you about the bond. But we have also looked at the force constant, for example, between the two bonds, and that also indicates that that also is consistent with what I have explained.
Okay, I agree with the fourth one, is probably a better measure all this density plots is always a little bit squishy, but this is in line with the fourth one. Okay, another slightly technical question, when you calculate the stabilities of the different dopings, slide 29. Well, I am wondering if you have the right formula there. I mean, usually when we talk about the stability of defects of dopants, then we take those dopants from the reservoir. So I would expect the formula invoking the chemical potential of the reservoir from where you take the dopant and into which you dump plunge or upstream.
Yeah, but here I think we were interested in the relative stability. So, like what we want to see the difference, the energy it gains or when it forms a new phase, new material, sorry, a new compound, let's say, new compound, then when it is its elementary phase. So meaning that the energy difference of the compound minus, here I am subtracting when this material in its ground state.
Yeah, I mean, that's what I read from the formula, but I don't think it's suitable to compare the relative stabilities when you change X, when you change the fraction of those. But for a given X, you can compare the stability of the different phases, that's very useful, of the different orders.
Yeah, I like depending on the concentration of the dopamines in each system.
Okay, we can discuss it some other time in particular. And a more general question, I mean, the predicted is negative, so big constants. And then it was measured. So how closely did you work together with the experimenters? I mean, did you just communicate the result and then they tried to grow the films and measure? Or did you really dive in detail how they do their film and how they do the measure?
we didn't guide them, but they and while I was doing these calculations, and we start trying to understand what is going on. And that time they have also measured the apnea sample, so that was not like we want some proof and we asked them to measure, but they found and then they contacted and then it was.
But what was first? They are the experimental finding or the observations? Okay, thank you very much. Now,
Yes, thank you. Yeah, so only quick few things to give context to Sangeeta's thesis. I mean, I think Sangeeta's thesis has been special in the sense that it's one of the first times that that I have been working on something that I didn't know much about before. We have done some work on the promotional patient hernia, which we found by using genetic algorithms, the previous course in the group. But actually, we have never worked about the zombie one, and so, for good or bad, this has meant that there have been so many places in the way and so many questions that came from the forward to which I just managed to the answers. Probably my answer, if I had one, was wrong. So this means that Sangeeta has had to deal with an unusual amount of uncertainty for what, if I compare with other PhD students work with me. And I think she has done a very good job at that, and I very much the way you presented this presentation with the historical, let's say, account. I want to say that we started, if you haven't mentioned it, that we started Sangeeta's thesis actually doing genetic algorithms to try to find new polymorphs. That was actually the first thing we wanted to do. Because we were still in doubt about how to define the topic, if you remember. And then we realized some people had already validated and that there was already a list of 50 polymorphs, and we actually didn't manage to make one particular algorithm to work. So we just spent a few months with that while we were defining the whole concept, and I was starting also to learn about happening. So that's very different from one of the cases where, at least in my mind, there is already a very clear strategy to answer the first question. And so I have enjoyed very much the journey, and I have to highlight your perseverance and ability to focus on to delay gratification while we were price after price figuring out that okay, we have to look at the first, etc. Another good example is the negative case response. So when we first saw this, I didn't believe, and we spent I think around 4 or 5 months computing with different codes in different ways, analyzing all the tensors. Finally, we saw that it was already published in the literature. So maybe, but that wouldn't mean anything actually, because it could be using just a code as the same as it was using a number, but it didn't explain anything, right? So, so again, another example where I think it didn't pay off. Statement on that, but that wasn't one hit, and I thought, I really have to say I was very happy to work with someone who was patient and worked hard to a particular objective and didn't get, essentially patient to try to understand what was going on. So, putting the priority where it has to be, in my opinion. And that's for the students. I don't know how useful or unuseful it is, how you have to manage in this situation, but I think that can be done very well. Beyond that, I think the ultimate results are quite nice, and you can be proud, of course. You really did all this stuff, and before we discussed a lot, but it's really your work. I think some of your answers here to this discussion have been a bit more brave to say some things. I think more or less have speculated about in our heads, but okay. And that's what I have to say. I really enjoyed the journey. And as I said, I think this at some technical level, it's not a difficult thesis, but when we look at the material and the surprises, it has been more challenging than most theses. And nevertheless, you managed to do well. I will not say very well. But I would say that they want to be moderate in this assessment. Yeah. I think you have managed to very, very well. And,
Okay, thank you, Harvey. So to our jury members, is there any other questions that came up that you would like to ask? If this is not the case, then the jury withdraws for some time. We try to be quick, but if we are not quick, it doesn't mean anything. So let's start with you back into this segment.
so I think we go maybe to our office. We need to know that virtual, okay? Very good.
Keep it right now.
Yes. Yes.
Okay, I still.
এটা ফাঁকা মাঠে
I told you,
আচ্ছা হ্যাঁ এগুলো একটু শুধু বললো পরে জেনে নেবো এগুলো একটু এতে যে তোমার ওই লেয়ারটা বলছে ওই লেয়ারটা সে লেয়ারটা
Because that means